Cool. So now, since we all discussed, the how Hadoop functions, Hadoop file system functions, and how we are going to we are basically, utilizing it for our use case, right? So we have to look back into couple of things that this Hadoop file system has by design, and you know they have some considerations too for us. We need to understand those constraints as well. The first major thing is disk-based storage architecture. So anytime we think about this Hadoop cluster, right? Um, Anytime we think about Hadoop cluster, right? Here, the node is basically a Linux box, right? This node is basically a Linux box, right? Linux box. That means this has hard drive, this has RAM, and this has CPU, right? So these three are the components that makes one data node, right? This hard drive, right? This is a mechanical drive, okay? Mechanical drive. That means every time you want to write data or read data from it, the disk has to spin and get your data. It has its own latency. It has its own operational overhead that comes with this kind of setup. You can say that okay, I can use SSDs here. Yes, even SSDs has some latency, right? They are not above this latency. It is, but it is much more better than the mechanical hard drives, since these are all digital. SSDs are all digital. These are less prone to this latency, but operational latency and all of that. But they still have latency. SSDs still have latency, right? Even the modern ones, right? So this mechanical disk itself is one of the bottlenecks that we can see in this particular architecture itself. Why did we end up with disk based storage architecture in the first place? You have to understand something here. All of the Hadoop systems, right? These are on-prem primarily. Okay. On-prem being that they are, built as servers in company premises, and they used to provide, the hardware, okay, the actual servers, okay, networking, okay, networking, cooling, and, the skilled professionals to like, uh, work and maintain these systems. This is before we getting to see any data in it. Okay, this is before any data professional even touches it. All of these are required. This is a heavy investment, right? And yes, people used to have servers on premise, and they thought that okay, this is a natural evolution at first, and they did that around 2000s. They had every company who wanted to do any sort of IT, they had their own on premise thing and everything that we discussed, that we mentioned here. Right. Hadoop was natural evolution to that because already the data warehouses were already present on the on-premise for large enterprise, servers. Right. But as soon as this cloud thing happened, around 2004, 2008 is basically when AWS was announced. That was the real, cloud, right? So when they announced it, there were a lot of people who wanted to upgrade them, and there were infra providers like Rackspace and all of that. So they didn't, not all of the applications directly moved into AWS, but they moved into these infra providers like, Rackspace, all of that, all of these companies, right? This is basically AWS before AWS, Rackspace, right? So what Rackspace did is, okay, I'll provide all of this. Okay, I'll do all the, and I haven't talked about software updates or hardware updates, right? Okay. They said, okay, we will just, okay, like throw all of this, bundle this, and we will say, okay, pay us, $1 million per year, $1 million per year. and we will take care of all of this for your hardware, whatever the capacity that you want. So that's what they said. And these on-prem systems got upgraded, and they started messing around with the Hadoop, like ecosystem, file storage, like map reduce jobs, all of this running in. This is at the what I what this is at the cusp of when internet is becoming a thing, right? That is how old these things are, right? That's why we see, like, most complicated architectures here. So to put things into perspective, right, I'll showcase you one good diagram or two diagrams. Basically, anytime you want to do something, right, you have to, like, let's say you want to, like, play music, or you want to, like, access a word doc on your like on your system, right? Your CPU has to do the calculations and then send it to your screen. Okay, right? And that CPU has something called as a cache that is built right on top of this die, which is really really fast, but this is only in bytes. Okay, this is basically in bytes, megabytes at max, right? But this is extremely fast, like extremely fast, hundreds of thousands of, like, like millions of times fast than compared to a hard drive, right? So this is built onto your CPU, bolted onto your CPU. Based on the importance of our application, we will use it, and CPU, like, does a good job of handling it, right? So this is one thing. The next thing is RAM. RAM is orders of magnitude slower than the cache, or L1, L2, L3 cache, or the memory that is available directly on the CPU. But it is even thousands of times faster than the hard disk or SSDs, basically, right? These days the hard drive, sorry, RAM and like SSDs are converging with the speeds, but RAM is still faster in terms, because we are storing the data in a place where we can access very easily, that is bolted onto the server, like very close to CPUs. So that's the advantage RAM has these days. So anytime you want to load an application from your disk, right? When you want to open an application, it has to load from disk. Okay, load it to RAM, and then CPU again. It has to do this CPU. Same thing with, this is fine for normal applications like music applications, your word docs and all of that. But we are dealing with data at petabyte scale. Okay, petabyte scale. Loading data from your hard drive is not an option at all. Even from SSDs that matter. We will discuss why this is the case when we are discussing with Hadoop MapReduce and Spark. But yeah, just understand that like loading any data from hard drive directly is not a good thing when we are dealing with petabytes of data. Okay, so here is another latency, like graph that I want to showcase in this section. What this is one black box here, means 1 nanosecond. So every time L1 and L2 cache, appears, right, we are spending around what, 4 and 7 nanoseconds. Anytime we are accessing L1 and L2 cache, that is bolted onto CPU's die directly, right? We need 7 seconds, right? And anytime you are, like mutex, there is lock concept. Basically, if you want to, let's say, access a resource without somebody modifying it mid operation, so we want to do some like locks. So that lock would take 25 nanoseconds, not milliseconds, nanoseconds to do, right? So 100 nanoseconds is one purple block, like that, right? So again, when you see, just reading, uh, like a 1 kilobyte over a network takes 10 milliseconds, right? 10 microseconds. So reading just a kilobyte of data from hard drive, I think it is somewhere here, it takes around 200 milliseconds, multiplied by petabytes, right, of data. So it takes a long time, right? So anytime it's not just like only Hadoop file system is cursed. But every single like disk based storage systems, right? They suffer with this latency. They will try to add more RAM, try to cache things, and then like reduce the latency of operations. But yes, anytime you think about a, any disk based storage, right? This is present. Okay. The other thing is storage and computer are tightly coupled, right? What do I mean by that? Here, when the data nodes are storing data, we are putting like very beefy CPUs here, right? Like really, really, really good CPUs, that can crunch a lot of data. But if we just want to like increase another node where, you can see that, you want to just increase the storage. We don't want to increase the compute because the compute on these, other nodes that are already present on the cluster are fine. That's more than enough for us. That we cannot do, right? Because if we change, we have to bring down one node, bring up one node. This is again like vertical scaling, right? We don't want to do that. If you want to just increase one capacity of one node, we'll add just one more node here. That increases both CPU and like your hard drive, just data storage capacity, right? We don't want to increase the CPU capacity because we have to pay a lot of money to the service providers, or we have to pay a lot of money to the hardware, and all of that again put on people to like maintain these stuff. It's not good, right? So we are just wasting a lot of compute or storage space. When we want to like increase one, automatically the other one will also increase, which is just waste of resources basically. There is no like way we can like reliably increase only compute or only storage without increasing the other, and just waste the resources along, right? So that is one more thing. The second thing, the other thing is worm model, right? Worm is basically write once and read many times. Okay. Mm, 1 second. Right. So this model was suited in, when Google released their paper, they said that, okay, this model, the worm means basically write once, read many times, right? This is very much suited for Google's needs, right? They wanted to like, dump lot, like, copy the website's data all around the internet and dump it at one place, which is fine, right? That is a lot of data, and they just want to only read the data and then create multiple data sets downstream. Not everyone needs this kind of data. Sorry, this kind of model of data updating. Give me a second. Sorry, I'm back. Right. So they have the need to develop this model, but not all companies need it. For example, let's say you are storing like 10 million images, right? You are an insurance company, you have to store some 10 million images or something like that, right? Or 10 million PDFs, images and PDFs. Not all, we can store it in Hadoop because this is a file system, right? you know but not every single item is like a block like this. All of these like will be under 128 MB at max. Maybe there could be one or two files that are more than 128 MB, right? And this creates a little issue because your name node has to like keep 10 million records, metadata of 10 million records in its RAM, which is basically creating a bottleneck, right? This is called as a small file problem in Hadoop, basically where you cannot just um, like put any amount of small files into Hadoop cluster and expect it to work fast. If you put if your cluster has like many small files, right, it will literally like eat your cluster's resources and the like general performance of the cluster very soon. So this is one like drawback to what we have seen in one model, or like in the model that Hadoop actually thrives at, right? And again, this is optimized for only high throughput. That means like reading like writing lot of data into it and reading lot of data, because that's where we get it cheap, right? Because the disk architecture, the storage, all of that is a bottleneck. Again, we cannot store a lot of data without increasing the compute, unless you have you are reading lot of data. Having this kind of resources doesn't make any sense, right? You are just wasting a lot of resources. And that too, it's a sequential read. It is not a random read, random access read, right? It is not a random read thing. It is just sequential access. That means, okay, let's say you have stored all of your images at one place, right? So directory one, and this is images one, right, in your cluster. If every single image is present here and you are trying to write, maybe run a machine learning model, all of this, so this is fine, right? If you are trying to like read randomized locations all the time, right, that means you are putting again pressure on disks that are underlying here, so which is a huge burden, right? Again, so this, we have to understand the trade-offs of the system very well before we think that okay, we know the system and we can use it. We cannot just you know throw the system into the at the problem and then like say that okay, this will work, and obviously it will not work, because yeah, the applications that we are seeing right now in big data environment, most of them do not agree to what the limitations we see here. Most of them, not all of them, but most of them, right? So that's what I wanted to highlight. Any questions here? I'll continue with the next three after you guys have any questions. Okay, cool. So the next big thing is like the replication factor 3. Not that it is any bad, or not that we don't want three copies all the time, but let's say you have 100 terabytes of data, like actual data. That means you are storing 300 terabytes of data, right? Because replication factor is 3. As simple as that, right? That means you have to buy 300 petabytes of terabytes of hard drives, plus at least 50 terabytes, or 10 to 50 terabytes of standby hard drives all the time, because anything could fail, right? This is a huge investment. This is a huge investment for any company, right? So this is not cheap by any this is not cheap by any means, right? What Hadoop promised was that we will be cheaper because it's open source and devs are contributing to it, and you don't have to pay licenses. But we ended up paying, what we missed on software and like contracts and licenses from closed source or proprietary software. We are paying it in like lots of resources. Doesn't make any sense, right? So that is one major factor as well. Again, when you see this, some architecture like this, right, these you might feel this as block diagrams and all of that, but these require a lot of skills to like bring just to get them up and running, maintain them, update them, not able to like have any security issues, and like reliably like making sure that every data request is possible on our cluster is a huge challenge. It requires entire departments, like as I said here, right? Whatever you are seeing here, right, this is not an easy one. This is not an easy one. Absolutely not. This is all of this is very, very, very like complex to a point where, like, not every company wants to take this up. This is a huge investment in terms of manpower, in terms of like physical hardware buying, in terms of commitments over the years. And right, even if there are some failures, the point people cannot complain about that. Right, because they are investing in that hardware, and what do they get as an ROI? They are not sure. So that's how complex these systems are, and maintenance and upgrades are really a bottleneck, right? Because you cannot bring down the cluster. Even if you bring down the cluster, right, it takes an hour to run. Do you think our sales team and marketing team will suspend their campaigns or their sales activities just because our cluster is down, or they are not able to find the right data when customers are literally like hounding them for their whatever they services they want, right? This kind of feels little troublesome to like even think at scale. So that's why Hadoop kind of dialed down back when the whole cloud revolution happened, and when this uh, object stores and S3s happen, and where cloud kind of said that okay, you don't have to worry about the hardware, you don't have to worry about provisioning, you don't have to worry about anything that we have like mentioned here, like any of these issues. You don't have to worry about that. Once you put the data in something like AWS S3 or any object store or Azure storage, right? You forget about the GFS or anything like that, right? You forget about it. Meaning you don't have to worry about the data durability, corruption, infrastructure going down, all of that. That's AWS's headache. What you will do is you will pay like $3 per a gigabyte of data just for storage. This is just for storage. Again, when once you access the data, you'll have to pay for the charges. But you get my point, right? $3 for 1 GB is a deal of a lifetime. Maybe now it might be like $10. Even $10 is not a bad deal, right? Considering we have to spend like millions and millions of in just getting the infrastructure up from someone like Rackspace. So that's how cloud won basically for data workloads. Interesting, not interesting? Somebody give a thumbs up or something like that. Okay. So now, cool. Right. Awesome. Awesome. Thank you, guys. Thank you. Right. So, okay. Hadoop. Yeah. I wanted to discuss one thing. When we said that, data, storage layer and our processing is completely coupled up, right? Like tightly coupled. I mentioned a word called tightly coupled here. What does that mean? Tightly coupled meaning. Tightly coupled meaning, as I said earlier, you cannot increase one aspect without affecting the other aspect. Let's say that you are planning a trip, right? Out of five friends, if one friend says that he's not coming, then the whole plan drops because the goal of you going to a trip is entirely dependent on everyone agreeing to it, right? So that's what basically is tight coupled, right? If one system goes down, the other part of the system is completely unusable. So that's the meaning of it. So there is an architecture pattern in the world that is called shared nothing, share everything shared and shared storage. Right? We have to understand this. This is a very important one, by the way. So your HDFS belongs here, right? Don't forget about DB basically. Let's say this is DN. Okay, this is not a DB, but it's a DN in our context basically. In normal application context, this is how it is, right? Right. What does this mean? There will be one master here. We Hadoop, like uh, understandably has master slave architecture, right? One we have name node and this one. In shared nothing also there will be one master. It will route requests to different nodes in the cluster. Anytime there is a some activity that is going on one particular like machine, right? It doesn't split its resources nor its data across different nodes here. That is called as shared nothing. This is an architecture pattern basically, right? This is what HDFS uses. This is what your all your Hadoop clusters uses, right? This is basically your Hadoop clusters. Okay, got it. So what happens in shared storage? Your application runs. Okay, there can be a master, there cannot be a master. That is fine, but your application runs. Every single node will access data from one single place. This is called as shared storage. Okay, this is your shared storage basically. Now, there is one more pattern that is your normal, like this is not a distributed compute. This is just one machine that has both your application and your database in one physical server, right? That is your shared everything. Because you have everything in one machine, you can literally say that okay, whatever that is available, that is for this particular application, right? So HDFS follows this. This is followed by Snowflake, right? At least on like Snowflake has both, both of them basically. Snowflake has both of them. On smaller, warehouses, it uses shared storage. On larger beefy clusters, it uses, shared nothing architecture. Snowflake uses, Snowflake famously uses, like shared storage one for smaller, warehouse sizes, right? Because it accesses data from not SanDisk storage, right, from S3. Okay, S3. And it can like spin up multiple nodes at once and then just access data from S3. That's how it is done. Any doubts here?
So here the nodes means the server compute.
Yeah, just compute nodes.
Okay.
Just compute nodes. What
Okay.
I can do is I can say that I can use latest Intel Xeon processor here, but I'll have only like what 30 GB or 10 GB disk internally for these nodes. This is basically just to store like runtime data. That's it. Just the operating system and runtime data. That's it. 10 GB or 30 GB. This is not used for data storage or anything like that. Okay, we will have Xeon processor. We will have like 1 TB RAM. Okay, but like 10 GB. This is just for storing the operating system and that's it. Nothing. But this storage is endless, right? Your S3 is endless, basically. Virtually, it is endless, right? For you. So every node that wants to access data will have to come to like this, cloud storage or shared storage, basically. Every single cloud data warehouses follows this architecture more or less. But Snowflake like famously like ground up built the into this architecture in the first place. That's why I've mentioned Snowflake first. Even Databricks does that. I'm not sure about others, but yeah, Databricks does that. Right. Any doubts here? Cool. Good that you guys are interacting. I'm feeling really happy. Cool. I used to always think that introducing these concepts will make the session dull, but since you guys are reacting, I'm getting little more ideas here. I wanted to include a couple of things more, but I was like no, let me just test this out and then we will think about it, in the future. Give me a thumbs up if you guys really liked it, or we should just skip it away. Okay, right, awesome. So what are object stores here? Object stores are not a cloud innovation or cloud invention basically, right? They are something what we call as network storage. Okay, let me just change my pen. Okay, what do I mean by that? Right, SAN storage, I think SAN or secured, I'm not sure, sorry. This is basically network storage. Okay, so in on-prem, systems, or in old age, like old age meaning like in older times when the cloud was not there, the data storage itself was something like we used to have just servers or hard drives connected with a proxy. Okay, this is a proxy meaning like it will route us to like relevant hard drives or storage spaces basically. That is a proxy. So our application is used to connect here. Let's say like something like a SharePoint, right? So where basically you'll have folders and all of that, right? Your app used to connect like this. So eventually this was like made since the storage capacity was getting higher and higher, right? The file fetching itself is little slow because we don't know which hard drive or which particular server or which particular place has which files. So they introduced another one called as, in the proxy itself they introduced another thing called as metadata, right? So metadata basically, when the proxy gets a request, it will check for the metadata and then it will route to storage. Here you might see that okay, this is exactly like HDFS, right? No, here the files will be stored as files. They might replicate the whole files itself, but they will like store files as objects. Okay, they'll store this as objects. They'll not break this as block storages. Okay, these are not block storages. Hadoop HDFS file system is a block storage. This is not. This is completely object storage. Like you will, if you have a 10 GB file, right, it will store 10 GB files at a place. That's it. And it will expose the 10 GB file through this proxy, through an API. Okay. They are very, very, very different. HDFS and S3 are completely different. Okay. For example, I'll tell you why. Anytime you want to like like we will see this in action in HDFS, right? Anytime you want to like like let's say this is a Linux system, by the way. You are seeing Penguin, right? This is an Ubuntu. Basically, it's a WSL kind of thing where I can install Linux within Windows. So this is that. This terminal is a Linux terminal. Basically, whenever you wanted to like do like file searches or list files, right? You would do something like this, ls, right? So something similar happens in HDFS as well. HDFS is a file system that is POSIX compliant. This file system that you are seeing here, this whole thing, the ls part is basically POSIX compliant file system. That means you can do CRUD operations, all right? Like create, update, delete a file. But you know the S3 file system is completely different. Since the metadata of the file, right? Since the metadata storage and the actual blob storage or the storage are at completely different places, right? And whenever we are interacting, right, we are interacting through a proxy. Your API servers is basically your proxy here. Okay, or sorry, your load balancers are your proxy, right? So anytime we are interacting with this, we will have some API here to, let's say, put or delete. Okay, we will have read also, but that is put or get and delete, right? These three APIs present here. That means when we want to like say there is no such thing as like create file, delete file, something like that. It is just put file, it is just get file, and this is just delete file. That's it. That's what object storage is. Object storage is very dead simple. It doesn't say something like that. But in Hadoop cluster, right, what happens is, as I told right here, when we are writing something, when we are writing, right, let's say I have it will choose one node, it will choose one node here to like say that okay, this is my primary replica, and any update that I'm putting here should go to secondary replicas as well. Okay, so whenever you are trying to write, a client is trying to write, right? If some reason second, when it reaches to second block, the write, same replica, second replica, it fails. Okay, it will revert it back, or it will not let the like that write happen basically. That's what it does. That's not a guarantee in S3. That is not at all. This is called as atomicity, by the way. This is atomicity, right? Atomicity. Basically saying that, okay, any operation that you are making, it will propagate itself to other files as well. Okay, that is not the case with S3, right? They have a different way of seeing things, right? Everything that you do here, it will be eventually consistent. That means that you will put a file, and if you try to read the file as soon as you put it, you will get the old file, or you will get to say that if the file doesn't exist, it will say that, okay, my file doesn't exist. After some time, it will eventually show up into that particular place. That is what it is. Any doubts?
I mean, didn't get. I mean, as soon as we put it, we can't retrieve it. Is that what you're saying?
Yeah. Not by default, but it is a possibility. Eventually consistent system means that, I'll say, let's say, you know, yeah, let's say you are, raising a request with your manager, right? In any ticketing portal for your, access approvals. It will happen, but it will not happen directly right away. So eventually
Yeah.
consistent system is that. Okay. So in Hadoop, what we can do is we can literally, whatever we are doing on like your in your Linux terminal, right? Let's say, ls, here we are doing some cat operation. Let's say, let me find some, yeah. Mm, right, we are doing cat operation. Cat basically means concatenate. It will just give everything onto the terminal. So these operations can be done. We are treating this as the same, no, we are doing this on a Linux system, right? We can treat the same in Hadoop cluster as well. I'll show it in a minute, but that's not the case with like object storage systems. Object storage systems, they will just store the data. Once you want to retrieve the data, they will give you an API, like, to put or to get or delete, based on what operations you want to do. And your application, has to do the reading and all of that. It is not a file system. It is just an object storage. Getting my point? Or still
Yeah.
okay. So what I will do is I'll share, this one with you guys. There is this wonderful, fantastic, this one blog post here by some, I think, this guy is called as Luminous Man. I've been, anytime I want to, refer a S3 versus object storage discussion, right? I'll refer to this particular one. So it's a good one. Yeah, I'll just paste it on the YouTube video description or in the channels, right? This is a pretty good one, right? So this is how it is, and I think we are almost done with our discussion for the day. We'll show, yeah, we will see the Hadoop cluster. Any doubts here, guys? I know I've been like literally over the top. I went over the top on a couple of things here and there, but yeah, we will see what's the difference, going along. Any doubts?
So money here, Databricks and Snowflake you mentioned in this
Yeah.
diagram. They
Sorry?
come under shared storage, Databricks and
Yes,
Snowflake.
because they modern, cloud data warehouses, right? They use object storages as their storage layer, not HDFS, right? They
Right.
use some aspects of HDFS, but yeah, not all of that. Okay. So let me talk about my, adventure basically here. I have created a GitHub repository. You guys can check it out. This is this one. So whatever you are seeing the architecture diagram, right? It is that. Is this diagram clear or do I have to like make it a little bit? Yeah, like this. So what I wanted to do was I wanted to like create a local Hadoop cluster for you guys to test and learn and run Spark jobs, Hive, all of that, right? So I prompted all of this to Gemini CLI and it recursively like fixed all of its errors and created this one, right? This repository, and here I have. So basically what it does is that there is, if you know about Docker is basically a lightweight VM. Okay, it's a lightweight VM, right? And basically, more or less a Linux VM, basically. Okay, most probably a Linux-based, VM, right? So what it does is it will logically create its own user space. VMs, we have to like, whole operating system will be there, all the file system, everything will be there, right? But in Docker, anything that is not essential, it will be stripped down, right? Based on that, we have, base Linux image. Based on that, we will install softwares and we will create one image. And on top of it, we will use this. So basically your Linux, right? Like Ubuntu. Okay. And this is your Java. And this is your, Hadoop, software, like application software. So all of this creates one container. Okay, Docker container. This is a very generalized, explanation, guys. Nothing rocket science here. Okay, this will create a one container. So what I have done is that you guys know me, right? I don't have like servers, at my disposal. So I wanted to simulate this environment in my own laptop, right? So what I did was I basically said that okay, Docker can do this. Docker is supposed to do this, right? Basically create n number of containers and create one network and then connect them. That is what HDFS, right? HDFS is basically that, right? Here you have your name node, you have your data nodes, right? So this is your HDFS cluster, although it is a very small poor man's HDFS cluster, but this is your HDFS cluster basically. Every time I do some operation on HDFS, that invokes this cluster basically. This is your HDFS setup. You can see this, right? Forget about all of this for now. I'll explain in the upcoming sessions. All the discussions that we are going to have in forward, right? In the upcoming sessions, we will use all of this infrastructure later on. Okay, all the big data stack is here. I've installed it, I've tested it. It's all working fine by God's grace. So yeah, we are good. We can like, literally like if you want to like, learn Spark, yeah, you can, just, install this project, Docker container and then up, all the instructions are present here, right? All the instructions are present here. So you can just, go there and, practice anything that you want, right? So yeah, that's what it is, right? So without further ado, let's do some, HDFS things. So this is my project, okay, that I created for this purpose. Sorry for the little interruptions. Yeah, this is my project basically. Okay, what does this project has? This project has something called as data. Okay, data node 123. That is my like data node, basically Hadoop data node. And this is the architecture diagram. What like what we have discussed right now. Yeah, that's here. The explanation is here. Everything is Gemini CLI, by the way, right? HDFS commands that you can check out here for your practice. What is happening, man? Right? So all of these are present here. Okay. And yeah, right. This is learning plan. Again, this is like how do you want to approach all of these systems. I'll update this going further, but you get the idea, right? What you have to learn, important topics and all of that, right? And yeah, examples, that is, I'll update it, as we go through each session. If you want to like go for Spark, okay, this is your Spark application. If you want to like practice MapReduce, I mean, nobody practices MapReduce, just for your idea, for your own idea, right? This is your word count example in MapReduce, right? And you know like your actual Hadoop cluster, the configurations of your Hadoop cluster. We discussed about like Hadoop, this one, right? Replication and all of that. Okay. Our current replication factor for this particular cluster is this, 2, value 2. By default, it's 3, but I know by default it's 2. We can, bump it up, right? We have, yeah, we have a lot of configurations and all of that here. And yeah, right. So currently it is running now. Here you can see, right, the Hadoop cluster here. So we have history server, we have name node managers, we have Spark, no, Spark container, we have Hive metastore, we have data nodes, we have name node here somewhere, yeah, right? All of this Postgres database for Hive, right? We will discuss all of this, why every single thing that is present here. Data node 1 and 2, you guys understand, right? Name node. This is basically your Hadoop infrastructure, right? Any doubts in that? Your Hadoop infrastructure is basically name node, data node 1 and data node 2 that you are seeing in this architecture, by the way, right? Whatever we have discussed in detail, in all of this excruciating detail, right? That is that particular one, right? This name node, data node. Yeah. Those are these name node and data nodes. This is a 2-node cluster, by the way. Okay. Right. Now coming to my terminal, right? I'll explain what it is going here. Since this is a Docker based environment, right? There are some prefixes that we need to have. Generally, when we are doing in Linux, right? So we are doing ls, we are doing cat, we are doing, cd, and then we will say, uh, you know, um, what folder do we have? Exploring Rust, right? Yeah. cd, and then we will say exploring Rust, and then, we will do an ls here. So we are getting all of these things, right? Which is fine. Like all of this is fine. We can do same operations on HDFS as well. This is just a simple Linux system within Windows again, but this is a simple Linux system. This is how you work with Linux commands. How do you do that in our name node or in Hadoop file system, right? Generally, what happens is we will do something like this. If you want to call the distributed file system of Hadoop, we will do something like this. 1 second, guys. 1 second. Yeah. This is all your Linux commands, right? Generally, when we when we are saying ls, we are calling our Linux machine to do a list of directories and files at that particular location, any location, right? This is just one single machine. How do you say that to a cluster? How do you say that to a cluster? Right? If you do an ls, it will do ls on that machine only. It will not do ls on the cluster, right? How do you do that? Hadoop has given our command line tools called, you know, is it? Yeah. Okay. HDFS, DFS. Okay. HDFS is your Hadoop distributed file system that we know. DFS means again, distributed file system. Okay. These are commands, by the way. Distributed file system. Okay. Okay. This is your prefix. This is your prefix basically. Okay. This is your indication that you are going to perform any operation, whatever operation that you are going to mention here on the Hadoop cluster that is a distributed file system. Getting my point, right? Here, let's say I want to do an ls operation. In Linux, it is just ls, right? That means list directories and files. Here it is -ls. So we are saying that, okay, we have an Hadoop cluster that is a distributed file system. And what we want to do is an ls operation. This is your ls, this is your operation. This is your file system operation. Okay. FS operation, FS meaning file system here, which is a distributed file system by the way. Okay. So let's say I want to change directory, or let's say I want to move or copy or make directory. Every single operation is prefixed by HDFS, DFS. Okay, this is your prefix. Am I making sense? Here we have seen this one, right? Like, doing an ls here. I'm getting files, right? Sorry, not here. Okay. Yeah. Here, when we see ls, we are getting files. When I say cd, again, I'll say, programming Rust, right? I'm in that C. Now, if I want to copy, this one, programming Rust into, Rust programming language, I can do that, right? With the cp command, right? Cp basically like, src, source folder or file, and, destination folder or file. If we give, these two values in normal Linux terminal, it will copy the files. Remove is, remove the file. These are normal operations that we do in graphical user interface. In Linux, we will do it on terminal, but in distributed file system, we will do it with the prefix. And here we are putting minus or hyphen here basically to say that, okay, this is the actual command that we should be doing on the on the distributed file system. So that's what it is. Now we will check that. Okay, we will see that in in action. Okay, so since this is a Docker based environment, right? So what I have to do is I have to always constantly call up my Docker cluster here, Docker name node here, to execute the command and then get me the data. So for that, right, I need to use something called as Docker exec. Docker exec, name node, because this basically Docker exec name node basically means that execute whatever the command that is coming after Docker exec name node on name node. Okay. HDFS, DFS hyphen ls and this, right? So now it goes to my, Docker folder or Docker system that hosts HDFS, and we are doing a input file here. See, these are all the files or file systems that exist on my distributed Hadoop cluster that is in my Dockerized environment. This is not in my normal file system. If I do say a simple ls here, right? Or even, Docker, name node ls, right? It is giving me a different result to what I'm seeing here, right? This is Docker name nodes, Linux box. Okay, this is distributed system that the name node hosts. Okay, let me clear that up. Here, this name node that you are seeing here, right? This is also a Linux box. Okay, right? So when I do an ls here, it's Docker exec, right? Docker exec, right? If I say ls here, this goes to just this, ls, this machine. But when I say, HDFS, DFS hyphen ls, this goes to our distributed Hadoop file system, this command. I know some of you might be feeling little over the head right now. Please let me know what if you have any doubts here.
So it will list all the files in the name node only, or like even in the data nodes and all.
Sorry.
So the ls command when you use the
No,
HDFS,
only on
DFS,
the name node. Only on the name
only
node.
on.
Only on the name node. When
Okay.
we are saying HDFS, DFS-LS, right? This is the data that is spread across all of your, data nodes.
Okay. So it
Am I
will
getting?
group all the data and show it.
Yes.
Okay.
Yes. 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 So because we want to scale the data sets, right? We want to scale the data sets. When we want to scale the data set, we don't want to put all of the data into one place, right? But if you want to access the data, files on all the machines at once as a logical entity, that's when we need this, markers saying that, okay, I want to list files on a distributed file system that is called Hadoop file system, right? So again, let's say I'll say raw here. Okay. Right. If I say, hyphen raw, it says, no files or folders, exists on name node. The second command failed because the, yeah, this command failed because it is executing on the single machine that is name node, Linux box. This one is executing on the distributed cluster on uh, you know name node, basically distributed Hadoop cluster. Am I making sense here, or it's all going over the head?
Yeah, I'm getting it. Yeah.
Okay. Darshan, Shashikant, Harshada, please. I know, I like, I'm yeah. Okay, cool. Right. So now you guys might be wondering, after all of this, are we just only like storing the data as is, and we are not doing any processing here? And even if you want to do it, how do we do it? Right? That is where something I mean, like normal programming, aspects doesn't work, right? Because you cannot put my Python program on all of this and expect it to run individually and then track individuals nodes progress and all of that. That doesn't work, right? Generally, when you want to run a program, right, what you will do is you'll have a Linux box, and within that you have a Python or Java application, and that loads your data from your SSD into your RAM, and it will process it, and then again if there is something to write, again it will write to SSD. All of this is happening in one machine. Okay, this is your traditional programming model. Okay, we are just storing the data here. That's it. If you want to run a compute a processing model, a program that processes data individually on this container, because I said, right, this is a shared nothing architecture. Anytime there is a data processing happening here, that is individual to each node. It is not shared across. There can be some data exchange in between, but they cannot share the processing in between between these two nodes, right? So how does this do that? There is some new programming paradigm called MapReduce. Okay, we will discuss that in the upcoming sessions, but this is what it is, right? So yeah, here I wanted to show one more thing. Yeah. So I have one more file called, this one, trip data 2025 and 01. This is around 460 MB of file. And when I say, there is a command called as a file check, right? I'll explain what does that mean, and I'll let you guys understand that, right? Since this is since Hadoop cluster is a like a file system, right? Normal file system, nothing like this one, nothing major or nothing like groundbreaking, right? They have a lot of knobs and controls to control the data, how it is being replicated, what's the um, you know what's the health of this one, and all of that, right? So for that, what I have done is I have listed some commands here. So earlier, there was a role called as Hadoop admin. What those guys used to do is, they used to do this file checks, balancers, all of these, right? What this means is that if you want to check the health of your file system, right? Instead of just relying on name node to always check it. If you want to manually check some issues there, right? We will do something called as FSCK. That is file system check, right? I've mentioned this here. So what we are doing basically here is that we are doing the same thing here, saying that, okay, go Hadoop, find this file and do a check on it. Check meaning what does it do? So it will give us the health. So how many racks we have? One rack. How many data nodes we have? Two data nodes. How many replicas we have? Two. Because our replication factor, why our replication factor is two is because we have only two nodes. If we had four nodes, right, our replication factor would have automatically went to three. We would have made replication factor as three by force doing it in the configuration, but that doesn't really serve any purpose. So all of these statistics will be present here, right, for every single one. This is what Hadoop data node will communicate to your um, name node every time there is a block report going on. Understood? So it has to if your cluster is 1,000 node cluster, right? It has to communicate all of this information for at least some newly modified files or some files that applications are touching or clients are calling. They have to literally send all of this data every time. So maintaining millions of files on the cluster will become a bottleneck in altogether after some point, because for every single block it has to communicate all of this data to the name node every 3 seconds or every 10 minutes. Imagine the amount of traffic it is sending within the within the cluster itself. It's mind-bogglingly complex, right? So this is what I wanted to showcase in this particular one. I'll stop the recording now, and in the next session we will start with MapReduce, which is a distributed processing framework and programming paradigm, which also led to creation of Spark and all of that. Yeah. If you have any doubts, please ask away. You can ask later as well.